don't know. Yeah, my advice is stick to the background, like life sci, because that way you can like it's easier, it's less a jump for you in this other stuff. Life science will be like this, and with linear algebra, there's like just like a mass, like with AI and genes, they do some like uh, I have some friends who work there, so they try to develop methods to do gene processing, and it's a lot of like AI and linear algebra statistics. It's just like so. Yeah, stick to your background because it will be less of a jump. It will be too stressful for you if you turn on like, and then over time you will pick up whatever you like. But if you're just gonna do it in like a month, yeah. Uh, yeah, I wish people were consistent. No, it's not the same because you can see it because you don't have linearity. It would be flipped. I mean, same result. I mean, the norm would be the same. The what orthogonality is the same because zero is zero, whether you take conjugate or not. But they're not the same object, obviously. Um, um, I don't know what to say. I mean, if there's yeah. It's not it's like when you pull out a constant, what is it? Come on. Right, when you pull out the there's a typo here, but there should be a B there besides the W. So there's a B here. So when you pull out the B, it gets conjugated. And the other thing you mentioned, it will be the A that gets conjugated. It will be like this. Whereas this one will not. Yeah.
Hello,
Yeah, okay. Thank you.
Adam.
All right, let's go. Yeah, I mean, well, I talked about the midterm stuff. This will be in it. Then we're going up to spectral theorem next week. But yeah, the emphasis will be inner products. Uh, yeah, 2.2, 2.7, the inner product stuff, the diagonalizability, and I mean, yeah, there will be some spectral theorem stuff, but it won't be too hard. So trying to think of what happened with midterm one, where we didn't really put a lot of coordinate maps because it was like right before. So similar thing. Okay. All right. Let's start. Projection map. So we talked about a little bit about representing bases. So you give me any vector v. If I know that my basis is orthogonal, so 0 inner product, then I can get explicit coefficients. And this operator here is called the projection operator. So over here. Okay. And what we just did is we projected on the subspace, on the subspace of the span. It was, what is it? It was the span of B1 to BK, right? That's what we just did in the previous thing. But this generalizes. So this happened to be V, but the same thing could have worked with any subspace inside V. So you give me any vector in V, I can find a basis representation in U. Okay? And what's cool about this? It's basically the minimal distance. So if you give me any other U tilde in U, you have that projection of V is less than U tilde minus V. I'm going to prove this in a second. Maybe next week, I'm not sure. But yeah, next week. Okay, we'll see. Yeah, this means that the closest vector to V inside U is its projection. It's like the smallest number, the closest, because it's a small number. So, some other U tilde could be over here. It's far. Projection is the closest. We're looking at this distance over here. Okay. That's all we're saying. All right, let's go. Yeah, it's called the orthogonal projection. What's my question? Oh, I don't know if you can do this. Do I prove it here? Okay. Now, let me ask you, maybe you can guess. So there's no basis here, right? There's no UIs on the left, but there are UIs on the right. Any guesses why this definition is basis invariant? How would you go about proving it? Like what? So what I'm saying is this is equal to summation of V BI BI squared BI 1 to M. Any ideas how would you? Oh yeah. Perfect. You come in. This is like answer the question. So what do you mean by arbitrary? Oh yeah, that's actually easier. Thank you. Yes. So yeah, let's do that. No. You're absolutely right. That's exactly that. Yeah, you just take one of them like this. And well, yeah, so UI, and then you use what do I want to say? Oh yeah, you extend the basis. That's right. Sorry. So you have to extend to n, the full dimension, which we are going to do today and tomorrow, called Gram-Schmidt. So you can extend to the full space. So this is n, okay? And then we do what he just said. So you plug that in here, and you get, where am I? Oh yeah, VBI, BI, let me call it K, because we're some BK UI divided by BK squared UI squared times UI. Okay, and yeah, thank you. And only m of them survive because so bm plus 1 to bn are in the U perp, which is going too far ahead. But anyways, we'll talk about all this. Let me just give you the flavor of it. I have to do this later again. This is too advanced for now. I'll come back to this. I'll just do the argument quickly. So yeah, anyway, so you only get, and then what do? You so you have an I sum, all right? You bring in the I sum. Okay, so you sum over I. So you leave the K outside. You have VBK, you have BK squared, and now you have the I guy. UI, but this is just BK because this is already in U. I'm gonna, because we just proved this, we proved that you can represent BK as the projections to a basis. We just proved that. Is that okay? So we proved this. We proved that we can represent. I know there's too many BKs here, but what we proved from here, we have BK is equal to the projections of BK UI, UI squared times UI. This is a same thing. Is that okay? All right. So, so going back here, you get summation of K1 to M, VBK, BK squared, BK. So, and right, we have a summation over I. So we got that this is equal to this. So you change the basis. The basis is irrelevant. As long as you have an orthogonal basis for the subspace, you can put anything you like. So it's basis invariant. All right. Any guesses? What can we say about V minus its projection? Yes. Yeah, perfect. So this is in U perp, meaning because if you take, I mean, we're going to prove it now, but projection of UV with, so you're projecting in U, right? So put U here. And yeah, let me do it. It's interesting. So I claim that this is 0. Okay? Claim. So let's do that. So we have VU by linearity minus projection of U V comma U. And what is this projection? Remember, it's over here on the, over here. So you get VU minus by linearity. You get this and then U, right? So how do I finish from here? Yes. Yeah, exactly. Also, I just want to see if people pay attention. Then you get big U minus big U, so it's 0. Okay, so this guy here, when you remove the projection of the vector, you get that it's in your orthogonal. So you have this beautiful decomposition, V1 plus V2 inside U perp. So we're going to prove this today. So you give me any subspace, you can split your vector into 2 components. Yeah, so let's start talking about this stuff. What's U perp? U perp is the space of all orthogonal components. So here I have an example. Yeah, let's start with this. So starting with this U guy, let's find the U perp using a dot product. Okay. So what does that say? It says W 100 is 0, and W by linearity, you just have to look at the basis. You don't have to like, and then 0, 1, 0 is also 0. So let's write W as ABC. So the first guy says you get the following system. You get A dot 1, B dot 0, C dot 0, 0, and you get B dot times 1 equal to 0. Okay? So that gives you that A is 0 and B is 0. So what is U perp? It's the span of what? Oh, just I want to see if I have it before. So this is the span of what? What's U perp? Huh? Yeah. Because C can be any number. There's no constraint for C. Is that okay? Yes. This should be what? Oh, yeah. Thank you. I'm so sorry. Yes. Ah. Yes, perfect. Okay. All right. So that's the U perp. That's how you find it. You get a system of equations each time. So many questions. Okay, let's do this one too, just to give you a flavor. So find U perp in the space of matrices. So namely trace of A transpose B needs to be 0. Okay. Then these four, I can be more specific. What am I saying here? So, namely, by linearity, just look at the span, transpose, and then A, B, C, D. Okay, you have to solve this system to get U perp in the space of 2 by 2 matrices. Okay, this is a very stupid, huh? It's a stupid example, huh? Yeah, okay, let me do it. So identity times this matrix is itself A, B, C, D, 0. So what's the trace of this matrix? Yeah, so A plus D is 0. So can anybody tell me what's U perp? Like what kind of matrices? Yeah. Oh, you want to do the span? Can you first tell me the form and then I will write the span for you? Perfect. Yeah. So thank you. So you take A, B, C real numbers like this, and yeah. So this is also the span of 1 minus 1 0 0, 0 1 0 0, and 0 1 0 0. Okay. So this guy is perpendicular, um, perpendicular to U, the span of the identity matrix. I mean, if you're not comfortable with matrices, you can do the snake transformation and go to R4. So U, so go to R4, go to R4, and then the isomorphic copy will be U tilde equal to the span of, so you have to put 1 0 0 1. And basically these guys are just the other stuff. So is that okay? I mean, I can deal with like 1 0 0 minus 1, 0 1 0 0. I don't know, it's not complicated. You can tell me if you. Okay, fine. So that's the perpendicular to identity. Right, let's do this one as well. Just to see that it doesn't have to be just numbers. So take this guy is P2R or P1. It doesn't matter. Just for PR. Oh no, yeah, no, PN. I picked my coordinate map. So this guy is a inner product in P and R. So namely, we have, you know, P0, P1x, P1xn, and you take gamma B of P to get the P0 to Pn. So then this guy is just the dot product of gamma B, gamma Q. So I think I talked about this, that if you give me the coordinate map, I can give you an inner product. All right, so find U perp. Let's find U perp. All right, what does that mean? Find the polynomials that are 0 with 1 and 0 with x. That would be U perp. So let's see, what is that? First component is 1, so P0, but all the other ones are 0. 0 Pn. So from here you get that P0 is 0. And same thing here, you get that P1 is 0. Do I have to do it? Is that okay? So you get that P is of the form, P2x squared all the way to Pn xn. So that shows you something interesting that, so the perp of U in Pn of R is given by these polynomials. So P2x squared, Pn xn in the field. Okay, so it matters where you pick your big space. If I said U in P2R, then U perp is a different animal. U perp will just be a P2x squared. You understand? So the ambient space matters when you form the complement. It's the complement in the ambient space. In the bigger space, yeah. Okay. Yes. Oh yeah. These are the right. I took an abstract polynomial. Can we consider? But I killed the X. Oh yeah, because I knew it. Let me do it. So from here you get P0. From here you get P0, 0 plus P1, 1 equal to 0. So you get that P1 is also 0. Because you need both. That's the U was the span of both. Okay, good. Yes. Can you speak up? Yeah, we can approve this exactly that you give me a subspace, its complement is the direct sum. So it makes sense to split into two buckets. Yeah, okay. Well, that's good intuition. Right, so, yeah. So this U perp is a subspace. I'm gonna put that now. And we already talked about projection and V minus the projection being a U perp. And we will prove what he just said, that you can decompose your space into U and the orthogonal complement. So that's what we will do for the rest of the class. So let's start with the subspace. So, proving subspace, you can do it with the closure criteria. But, we're adults. No, this is still adults, but we learned some stuff. So how would you prove it in a different using this linear map? Because we're going to see this map again. I just want to prepare you. So I want to prove that this is a subspace and this is a linear map. And you see a 0 here. What's the natural order? Yeah, exactly. So, but we're not there yet. So can you tell me a way to, so the kernel of TW for fixed TW, like small w, is all the V's in V, so that VW is 0. But we want for all W. How can we get all W? This is something you learn. No, something, no. Because we want all W. How can you get all mathematically? You have a bunch of spaces, but no, close. No, because the more elements you add, the smaller the U perp becomes. So like the U perp of these two is 0, 0, 1, right? Yeah, intersection. So intersect over all W in W, and you proved in your homework or something that this is still a subspace. Does that make sense? I wanted to put everything learned in like one line. So this guy is a subspace, and intersections of subspaces is still a subspace. Okay. Right, yeah, so when you intersect, you're forcing exactly what you said. You're forcing all the V in V, so that VW is 0 for all V in W, W in V. Yeah, okay. All right. What am I doing now? Oh, I'm proving this projection stuff. Okay. Yeah, so I'm going to prove this. Right. So we say fixed orthogonal basis, but hopefully you can challenge me with that. How do you know it exists? We do not. So we will have to prove it today and tomorrow using Graham-Smith. So we proved basis existence like 4 weeks ago. Now we're going to show orthogonal basis existence. So wait, we will come back to it. Graham-Smith. Okay, so but assume you have it. And let me remind you what the projection was. So you go from I 1 to k, and you project your vector in every coordinate. Can someone tell me why is this in U? I know it's immediate. I was just telling you. Yeah, but just from the definition here, why is it always? Yeah, okay, thank you. That's all. I just wanted to hear a linear combination. I just want to see if everybody's happy. So that's why this is in U. Good. All right, now let's do the hard stuff. Let's show that this is in U perm. I did it for one vector, but now I have to do it for all of them. So yeah, I think, yeah, we did it for one vector. Now we have to do it for the entire subspace. All right, let's do it. So namely, you give me any U in U, I have to show that this is 0. Okay. Right. We just did it before in the case of U being a single vector, U, before. So if you want to look at it. Anyways, let's go. So that's what we're going to show. Step 1. Okay. By linearity, you can go from here to here by linearity. Okay, in the first component. So there's no conjugate. Yeah, I built my proofs so that I don't have to look at conjugates all over the place. So yeah. So you do this first, and now you can take out the summation again by linearity. Okay. Good. Do I have a question here? Yeah. What can we say about BIU? Any ideas? Like, what is it equal to? Very specific. Yeah. You know what U is. So what's BIU? Yeah, it's just AI. And yeah, so let's do that. So if you put this together, let me do it. Doesn't matter. So BIU. Let me do it the other way, we'll contribute later. So UBI. So you have summation of M1 to K of AK, BK. No, M. BI. Then you use linearity, you bring everybody outside. BI, but these are all orthogonal. So you're left with delta MI. So you're left with AI. Okay. And if you conjugate, you get AI bar. All right, it's okay. All right, so anyways, we're taking zeros. We want to show this is zero, so I'm not too worried about the conjugate. Okay, so again, we use linearity, so we have this u, and we just said what BIUS is this AI. Okay, so just to be clear, we had where am I? Yeah, I missed something. Yeah, so it was. Let me fix it over here. In my notes, it was okay. In my calculation as well. So it's not orthonormal. So you still have BI here. So it's AI BI squared. So this is BI squared. Yeah. Okay. If you have a question, please tell me. So you come back, and this is where the BI came from. So this here is equal to this. Okay. All right. Hopefully I have the question here. Oh, I did it. Damn it. All right, fine. I'll do it. So the same thing as before. We have cancellations here. Okay, so that's why you're left with these two, and you get zero, which is what you want. In other words, V is equal to V1 plus V2 with first guy in U and second guy in U perp. That's all we proved. There's nothing fancy here. You don't have to get overly right. So now let's prove this result, namely that you give me any subspace, I can decompose. Okay, so we just showed that if you give me any V, I can write this as projection of U or V in U, and then minus the projection of this, right? I mean, clearly these two cancel out. So it seems like we did nothing. But the point is, we just proved that this guy is in U and this guy is in U perp. Is that okay? Good. All right, so you have the decomposition, but how do you know that you have direct sum? Before I go to the next slide. So how do you show direct sum? Yes. Yeah, that's all, yeah. So we need to show empty, that intersection is only zero. So suppose otherwise that you have some X in there. I don't know, before I go to the next slide, does anybody know how to get that X is zero? Oh no, wait, yeah. So U perp means what? All the W so that VU is zero, right? For all W in U perp, for all U and U. So how can you use that? If you know the X is in both, what's the implication? Yeah, go ahead, yeah. Well, first apply the fact, then we'll go from there. So if you apply this fact, you get what? You get that x is 0. And then that's just the axiom of positive definite. The only such element is the 0 vector. Yeah, everything. Yeah. So that's how we get empty intersection. All right, so we proved that you give me any vector space, I can always split it into 2 parts. And the same thing we will show for the basis, right? So you have U1 to UK and then I don't know, some span UK plus 1 to UN. This guy is for U, this is U per. So complete like the buckets he was talking about. You can split your space. Right. So today and tomorrow we'll work on this. You give me a subspace. I said fix an orthogonal basis, but you challenge me. How do you know there is such a basis? So we have to use something you learned in 223 called Gram-Smith, but we're going to do it for abstract vector spaces. It's the same proof. You use dot products, we're going to use projection maps. We did this, right? In 223? No? It was in your book. Maybe, no, he called it. But you remember when you built an orthogonal basis? I mean, I remember looking at it was the same, like removing dot products. I remember looking at this. Okay, I'll take a look. I can't remember, it was like, we probably did like half a day. Right. Right, but we saw the existence of a basis using the augmentation lemma. Now so we have a basis, at least I have the span. So you don't have to like try to span the space. So you have the span. Now we're going to build the following orthogonal vectors. V1 is always V1, whatever your V1 is. And then this is an inductive argument. So up to L, for any L, for a fixed L less than K, you assume you have orthogonal vectors. So Bj, Bm is 0 for Jm less or equal than L. Okay? So assume you have this. This is an inductive argument. So assume you have this. Here's how you represent BL plus 1. You take your VL plus 1 and you remove the projection of the previous space. Can somebody tell me in what space this belongs? This BL plus 1. Can you tell me? I'm not sure if you can. Yeah, you will probably, yeah, thank you. Yeah, of course. Yeah. Okay? All right. So you define it like this, and we're going to prove that this is still a basis, and it's also orthogonal. So inner products are 0. Okay. Yeah, and this process is called Gram-Smith orthogonalization. You start with some bases that you're interested in, and you can create the orthogonal copy that's close enough. Because after all you're doing, you're just subtracting a number. Okay, it's a little bit more complicated. All right, yeah, so we just showed that this is in UL perp. So orthogonality is immediate, right? Because UL, let me remind you, UL was the span of the first L, B1 to BL, right? So right away you have orthogonality. So BL plus 1 in UL perp means that BL plus 1, BI is 0 for I and 1 to L, right? Okay. All right, so orthogonality came for free. I have to show that you didn't lose any of the spanning stuff. That you can still span the whole space, U. Because when you remove the projections, maybe you somehow lost a vector, maybe they became linearly dependent. I don't know. How do you think it's going to happen? All right, let's do it. So again, by induction, assume that you have the L case, so that these two spans agree. Okay. And UK is U, right? So we have U1 is inside U2, UL, and now we can approve the UL plus 1. And then because L is arbitrary, we're also getting the UK or U. So this is an inductive argument. We're proving it for every L. What's that all? All right. So we want to show the same for L plus 1. And can someone, where's my question? The question is here. Yeah. Why, by showing these two, you get this? Again, this is just to see if you're following or the complicated. So let me ask you the following easier question. What does the first thing imply? So you have span of BI I1 to L plus 1, and then you have span of VI I1 to L plus 1. Which inclusion does the first guy give? Left or right? So, wait. Can you guys do with your hands? Is it this or this? I see. Why this? Oh, like, damn it. Okay, wait, right. So it's this guy, right? Oh, okay. I see. Yeah, sorry. All right, perfect. I was like, what? Good. And yeah, this is the, yeah, and the other one's the other one. All right. Oh, yeah, okay. So we want to prove that BL plus 1 is in the span of U what is it? Yeah, of this V stuff. V1 to VL plus 1. So this is a summation, right? This plus minus that. This guy is 1 times this, so it's in the span. And this guy is in UL by definition, because you're projecting in UL. So, yeah, and so this is, you have a summation here, and then this is inside what? What is inside these two sums? Or inside what? Yes. Sorry? Yeah, it's inside the span of all of them. But okay, oh yeah, let me ask a simpler question because maybe you're, I mean, there's a middle step here. The UL, what's the relation of, so we want to say that this is inside the span of all of them, but how can I get this? How can I use my, let me go back a bit. How can I use my induction to do this? Wait, yes. Yeah, this is our, I mean, okay, UL is this, right? But by inductive hypothesis is also that. By definition, this is UL. By induction, this is what it is. Okay. So this guy over here is the span of VL plus 1 plus span of V1 to VL, which is exactly this. Good. All right. Yeah, so I will finish that. And now let's show that the other inclusion, that this is also in the span of B1 to BL plus 1. So we take the same thing from here and we just rearrange. So we brought the projection to the left. Okay. I mean, okay, we just talked about it, but the UL is by definition the span of B1 to BL. So when you take them together, you get the whole thing. Okay. No, we want to show that. I said we want to. Yeah, because like you guys said, right? The first guy gives this, and then the other guy gives this. Yeah. All right. Almost there. So yeah, let's play with it. Let's get some examples of doing Gram-Schmidt. So I will start with R, and tomorrow I'll do with polynomials. Okay, I will continue tomorrow. Thank you.